All right, the last part of chapter 4, or chapter 7, sorry, 7.4, applications of simple harmonic motion. Okay, this is a shorter section. Okay, but maintaining a pendulum's resonant frequency. So what resonant frequency is the natural frequency of vibrations of an object. Okay, and so like to think about like resonant frequency, like as you walk, your arms swing. That's your kind of your natural frequency for the way your arms move. Okay, when you're pushing your little brother and sister on a swing, okay, as it goes up and down, okay, as they kind of are doing it on their own, that would be their natural resonant frequency. So to compensate for friction in a clock, so the way some of these clocks work with a pendulum, it kind of goes back and forth, right, at a resonant frequency. But there's friction in the gears that would cause it to stop. So there's a mechanism in a pendulum clock which is basically it gives it a push that coincides with its natural resonant frequency to keep it going to the same height each time. Okay, and so that would be our force frequency, is the frequency at which the external force is applied to a resonating object. So mechanical resonance occurs when the force frequency matches the resonant frequency, and so you get a larger and larger amplitude of vibrations are the result. So again, like if you think about pushing a child on a swing, okay, you get them to a certain height. If you want them to go higher and higher, you have to keep pushing, add in this force frequency, and you want to push them like as they swing up, you're going to push them down. If you kind of, as they're coming up, you're pushing them down, it would not work. So you kind of have to, it has to go along with their resonant frequency. You have to match that and then add the force frequency to it to get them to go higher. Okay, and so kind of a little way to look at this flow chart. So is the force frequency closed to resonant frequency? So we'll start with yes. So if it's closed, a small force is required to keep the object vibrating with the same amplitude. The force is increased, the amplitude of the vibration should increase. Okay, if it's not close to a resonant frequency, then the amplitude of vibration is not increased or maybe decreased. Okay, and so the effect of, or this is looking at the effects of force frequency on resonant amplitude. So really, like if you stop pushing the person on the swing, okay, then the force frequency is not close to the resonant frequency. So because of friction, the swing's going to eventually stop. Like they get lower and lower. Okay, if you have it so that your frequency that you're pushing is at the right frequency or matches the frequency of the swing, then it can continue to get bigger. And like if you do the underduck and stuff, the force will increase and the amplitude will increase. Okay, different buildings and bridges have different ways of accounting for resonant frequency. So you got to think like this is made out of all these different materials, and they're a little bit elastic. They actually allow the building to lean a little bit, because if they didn't and you got any kind of big winds or earthquakes, the whole building's going to crumble. So you want it to be a little bit elastic where it moves from side to side. Okay, but the problem is like if you have, like it's going to move naturally side to side. If all of a sudden you have a wind that comes in and matches that, it's going to move even more side to side. So you want to make sure that basically your natural resonance, your natural resonant frequency does not match the mechanical resonance, or else it'll cause the building to break or a bridge to break. Okay, if you watch the videos that I kind of post along with this, I know it's 23 minutes, but if you watch a bit of it, it shows a bridge that kind of undergoes that resonance and ends up breaking due to the winds. Okay, and so what buildings do, they have this dampener in them, so a large weight right near the top. So as the building moves one way, this weight moves the other way to kind of go opposite of the natural resonance to basically prevent it from swinging so far from side to side. Okay, and so as it pushes one way, this counteracts it and pushes the other way. Okay, and then they can adjust the cables. If it's a windier day, they might need to get it to swing more or less, and so on. Okay, quartz clocks. So again, like the kind of the original clocks were pendulum clocks, and they had different types of weights and stuff in them. Okay, now like we aren't gonna have a pendulum and put it in our wristwatch and have it move inside the side. Instead, what we have is these quartz watches. So what quartz watches do, they have this quartz crystal, which then they're shaped into the a quartz oscillator, and then as electricity is put into this, it makes it vibrate at a certain frequency. Those vibrations, okay, then control all the mechanisms inside that clock.